Devi limitare la discussione, sound out. Mi piace
Rendere su mail.
ma appunto mi piace ma non è rendere su mail. Come ti piace? Deve essere disattivato. Perché te l'ha fatto, no?
Ci riuscite perché sono ossessionati di
Ciao Gianni. No,
Sì, si sente tutto. Adesso mi sto girando. Ok, sono girato. Però tu devi disattivare il microfono. Ok,
vado su YouTube o su Radio Loggione.
perfetto, così. Adesso mi dovresti vedere.
Ah, sì.
Sono io che sto riprendendo.
Sai come vado di noi streaming?
Però io vorrei vedere me stesso.
davanti.
Ma no, perché io vorrei
filma il film.
Io sto riprendendo con questa.
Filma il film, così ti vedi?
No, cioè volevo vedermi da qua. No!
Aspetta, perché ho...
Però è stato...
Così a un certo punto potrete attaccare.
ma in teoria... No, non va.
Però lì
Perché non va? Perché voi non siete in grado. Ma anche il video volete fare, ma non si può fare il video.
Come no? Lo stiamo facendo. Perché poi mi dà... Ah, ma no,
Sì,
forse
ma non
ci
si può
sono.
fare il video mentre lui discute. È vietato, è illegale.
Ma io ce l'ho qua in tasca il telefono. Sì. Dal sito. Scrivi Menti e Genti, Radio Loggione, ci arrivi. Sì. Però io qua non mi vedo, porca vacca.
Quello che sotto l'altro erano pagine cosa avevi fatto? Avevi toccato? Poi era sparito qua.
Sì, disattivato. Io qua però mi vedevo.
Allora, il problema è che sì,
Fai un saluto a Radio Loggione che sei in diretta.
Salutare Radio Loggione per questo grande evento di Baccarini che si laurea, ma soprattutto la vera domanda è dopo cosa va a fare nella vita?
Oh, l'ingegnere cattivo. Sei in diretta su Radio Loggione.
Finalmente mi sono stata invitata.
Ah, è vero che lei non ci può, scusi,
Devo
scusa.
invitarla perché nessuno mi sfila, quindi...
No, ce la devi fare, sono 200 puntate che ti dico come si fa.
Sono troppo. Bisogna aprire il redettivo social club Menti Agenti.
Cerca Menti e Genti.
Cioè dal mobile non riesce ad entrare nel nostro sito. Dov'è? Ah, non ce la fate anche voi,
Questa roba.
ci ha provato.
Se vuoi ti do proprio le mie credenziali se
Ma siamo già entrati. Non lo so.
Andate la ferro che lo segue per me.
Però Vacca, com'è che si dice? L'altra volta io vedevo da qua, perché adesso non vedo più?
Sembra un momento. Ma ti sembra un momento? Mi sembra un momento.
Beh, ma lo devo un po' disattenzionare, perché sennò...
Guarda che sei serio.
Cioè, Johnny, la prossima volta ce la prendiamo più con calma.
Sono andata a prendere le birre col passalato.
Quindi non c'è in diretta.
No, c'è. Solo che io non vedo quello che inquadro, quindi... faccio fatica.
Ma dov'è il...
Eccolo, eccolo, Laurea BH.
Sì.
Trovato. Come faccio a prendere...
Eccoci. Si sente tutto quel che dico.
Come faccio a prendere il link da qua? Dicevamo?
Condividi? Apri il link. Su WhatsApp sto cellulare chi
Sì, devo stare concentrati.
È vero, sì, non prendo. Non prendo, sì. A parte il wifi.
Ah, ma io c'ho ancora le mie credenziali della UNITN.
Puoi andare... Allora io sono Facebook allievi e fai finanza.
Ma dai, ma tanto non sappiamo neanche. Io non posso
infatti volevo ringraziare.
Ci vorrebbe una taschina che uno se la mette qui.
No, nessuno, forse Lolla ce l'ha.
Aspetta.
Se meglio.
Ce l'hai un taschino.
Tieni la camicia. Sì. Camicia seria, ragazzi.
No.
Tieni così. Aspetta,
So we start with a brief outline. I will start introducing what are aerosols, why they are important to the climate. And then we speak about the location that is the hazels, so why it is important to study the aerosols in the hazels. And then I will go through the physical basis, the experimental apparatus that is my instrument background, and finally the results in the conclusion. So let's start with aerosols. Aerosols are tiny particles suspended in the atmosphere that directly influence the climate by means direct interaction with the solar incoming radiation and the outgoing infrared one by scattering and absorbing this radiation. And they also have a secondary effect, that is they act as cloud condensation nuclei, and since clouds have a strong albedo, they play a major role in the determination of the balance of the Earth. The IPCC, that is the Intergovernmental Panel on Climate Change, estimated that aerosols contribute to the larger uncertainties on the overall relative forcing term, that is the measure of how much the various drivers affect change, are able to change the temperature of the Earth. And thus this can affect the overall accuracy of the climate models. Why aerosols why the determination of aerosol effects is so difficult? Because they are extremely heterogeneous in size. You can see here that the particles spans from few nanometers up to tens of micrometers, and in size. These are particles, images of particles collected at the Common Observatory. You can see that they change significantly between one and the other. And then they are also heterogeneous in terms of spatial and temporal variability. And this is a model from NASA that shows the different kind of sources, and you can see that they are not homogeneous. And for example, there is CO2 that is one of the major driver in climate change, is well mixed all over the atmosphere. And the azoles are a key place to study the aerosols in the North Atlantic Ocean. They are the only place that is representative of the North Atlantic Ocean. They are downwind of North America, and this means that in the majority of cases it was possible to measure aerosols coming from the North America. In particular, this study was done in Pico Island. It is one of the 9 islands of the Azores, and its particularity is that it's dominated by the tallest mountain of the whole Portugal, comprised the continental Portugal, the Pico Mountain, that is about 2,300 meters. And for this reason, on the top of Pico Mountain, and this is the Mount Pico Mountain, this is the top of the mountain, this is Casa Montagna, where they hike to go to the top star. And for this reason, in 2001, it was established a station on the top of the summit caldera of Pico Mountain to measure long-range transported aerosols and trace gases. And the idea is that the station lies typically above the boundary layer, that is the part of the atmosphere that is directly influenced by the surface, and thus it allows to study long-range transported aerosol without contamination from the surrounding, that is the local pollution, that in any case is minimal, because the Azores have extremely clean air, but also from the sea salt aerosol, that it would be one of the main contaminants. And so, if there is the station, where is the values of microfiles? The values is in the fact that these measures are complementary to the station, and in particular, one of the main aims of my work was to understand whether, and under what condition, the station is effectively above the boundary layer, and so to investigate the presence of possible intrusion of air masses from the boundary layer up to the free troposphere or vice versa, and also to have an overall understanding of how the properties of aerosol changes across the verticals. And this would be important in particular concerning the free troposphere, because in the free troposphere, as we will see in a moment, aerosol tend to stratify, and their properties are generally not well known, and that this could improve the overall our overall knowledge of their climate forcing term. That's only a note about the field work in Pico. I would like to point out the fact that doing a field work is really different compared to doing an experimental work. In particular, the number of measurements that I was able to do, it was limited by the weather, because on the mountain is always often affected by bad weather, and even if from the outside a wonderful lenticular cloud appears on the top, doing a profile inside that cloud is not beautiful, because it is characterized by extremely harsh conditions. And this is one of the main limitations of this work, and also the fact that the hiking is not easy, and so I wasn't able to do it every day, and so even if there was maybe a window of 5 days of good weather, I could do it maybe only 2 or 3 times. And finally, also the fact that this project was not covered by any specific fundings, and so I had to spend a lot of work in order to try to understand the validity of the measurement that they did, and to estimate the values of errors. So let's start with a small introduction about the boundary layer. I won't go too much into the details, but only to give you a feeling of what is the difference between the boundary layer and the free troposphere that is above it. The boundary layer is a region that is in which there is stark turbulence, and in which vertical mixing is allowed, in particular an unstable region. On the contrary, on the top of the boundary layer, it's the free troposphere that is only very stable. stable, and this means that vertical transport is not allowed, is inhibited, and particles may reside there for long times because there is no turbulence, and thus they are not dissipated like in the boundary layer. PMO, the station lies above the boundary layer, and this could be easily seen in when there are condensation conditions because there is a clear layer of clouds which A does not change, and this is also evident in this small video. Now you will see if it works or not. And in the videos we see that as expected, it doesn't work. In the video, it was shown the fact that even if the horizontal dynamics is present, clouds in the vertical don't change. And here, there is one of the five. In this case, it is interesting to know that here the relative humidity have sudden drops when passing from the boundary layer to the free troposphere, and this was one of the ways to identify the boundary layer. Study of the boundary layer in the ASOS have already been performed, but they were done based on radio sounding that is in free atmosphere conditions, so they were not influenced by the orography, and it would be important to understand whether the orography changes the heat of the boundary layer. They found values in the summer typically between 1,000 meter and 1,300. We did the same with our instrument. We will explain this better later, but we found values that are slightly higher as expected because during the day the heating of the mountain should rise the heat of the boundary layer. And so after this brief introduction about the vertical structure of the atmosphere, I will speak about only a few definitions about scattering and absorption, just to be sure that we have the common language and we do not misunderstand. The scattering perception, as you know, is the fraction of power that is removed from the incoming beam by means of scattering and absorption, and usually we call extinction the sum of these two terms. The single scattering albedo is a term that is widely used in relative forcing studies because it quantifies the probability that a photon interacting with a particle is scattered rather than absorbed. Thus, a single scattering albedo near to 1 means that the particle is strongly scattered, strong scatter, and it doesn't absorb, and vice versa when it is near to 0, it is the opposite. The phase function is substantially the differential scattering cross-section normalized and gives us an idea of the angular pattern of the light. The scattering coefficient is a quantity that is substantially the cross-section multiplied by the concentration of particles inside the scattering volume, and it is more widely used because it can be directly measured by means of an accelerometer, that is one of the instruments that I bring in the backpack, and it can be interpreted by means of the simple Lambert-Beer law, that is light is attenuated by a factor that is proportional to the extinction cross-section passing in a slab of atmosphere with a thick X, and so the units, you can see that there is an inverse of a length, and the multiplying factor is usually a 10 to the 6, that is, as you will see, there were the units of inverse megameters. And finally, the atmospheric optical thickness is the integral of the extinction coefficient from the sea level up to the top of the atmosphere, and is a measure of how much the light coming from the sun is attenuated in passing through the atmosphere. And finally, the angstrom exponent is substantially semi-quantitative law that is used to describe the power dependence of the atmospheric optical thickness, that is of the extinction cross-section, and it is useful because it can be used to evaluate the volume, the size of the particle. In fact, in case of particle much smaller than the wavelength, we recover the theory of Rayleigh with an exponent of 4, while for a particle bigger, we have a smaller exponent. As you can see here, mineral dust has an exponent around 0, while soot is 2.5. I also want to point out some values here in Beijing, that is an extremely polluted region. We have a scattering coefficient of around 900 megameters, that is, the light is attenuated by a factor 1 over E after passing through more or less 1 kilometer of atmosphere. We will see that in the ASOS, these coefficients are more than 1 order of magnitude lower, and this causes some problems concerning the signal to noise ratio. So let's move on. This is my experimental apparatus, that is the backpack. You can see here the shelter that was adapted in order to cover the temperature, pressure, and the reactance sensor from solar heating. This is the sun photometer that was used to measure the aerosol optical thickness. It measures the aerosol optical thickness at 5 different wavelengths that covers more or less the whole visible spectrum. And here inside the background there are the nephelometer and the particle counter. I will review briefly the main analysis. This is the number of profiles that we acquired in both the seasons. Consider that these are higher than the others because it was the only measurement that could be performed also with the weather conditions. So very briefly, this is the brief description of the sun photometer. In particular, sun photometer measures a signal that is proportional to the solar radiation, and if the zero is the extraterrestrial constant and is determined by a calibration is known, this constant is equal to the signal that could be measured on the top of the atmosphere. R squared is the distance between the sun and the Earth in astronomic unit, and M is the relative air mass, that is the optical thickness of the atmosphere normalized in a way that when the sun is overhead is equal to 1, and when the sun is at the horizon is maximum. Tau is the overall atmospherical thickness, and it is made by several contributions like ozone absorption and molecular scattering, and the retrieval of the aerosol optical thickness is not straightforward because there are several corrections must be applied. To determine the extraterrestrial constant, a Langley calculation is done. That is a measure of the signal as a function of air mass. So during half of a day, one takes a lot of measurements at different hours. So to these each line corresponds to one of the wavelengths of the instrument, and you can see that the correlation coefficients are pretty high. That means that the calibration was properly done, and that the measurements are supposed to be reliable. And this is a comparison that we did with the nephelometer in Graziosa. It is an island of more or less 70 kilometers far from our island, so some differences are expected, but we can see that the point at the measurement that I did, while the lines, so the lines here have the measurement of less than kilometers, you can see that more or less the signal is compatible, and the difference of intensity is probably due to the fact that they are near an airport, so the level of pollution there is supposed to be higher than in people. And this is the nephelometer that allows to measure the starting coefficient. It works at 530 nanometers, so only one wavelength, and in particular it uses wide-angle sources with an opal glass reading the direct intensity following up to any load, the American source, and this allows to integrate over the whole angle to measure the single starting coefficient. We did several comparisons. Here I report only one of them with the another nephelometer at Picomon and observatory. You can see that even the dynamics of the signal is not very high. And is near the signal level. The two signals is good, and they also would like to point out the different values. Here we are around 10 inverse megameter. That is the light is estimated by a factor 1/p after passing through 100 kilometers. So the signals are effectively small. While, for example, in the Covale, the signal is typically between 1,250 and 500. So you can see that there is more than 100 magnitude of difference. And this is a correlation plot. Clearly, the dynamics of the signal wasn't very high, so the correlation is not perfect, but at least the slope is near 1, and the intercept is different from 0 because there was probably a problem with the 0 setting. But however, this error was estimated to be more or less under the 20%. The total signal. And I would like also to point out the fact that in our cases, what we are interested in is not the absolute values, but the relative changes. So even if a systematic errors affect our measure, is not important like the fact that the dynamics must be reproduced. This is the scheme of the optical particle counter. It is properly tuned to count particles up to two different thresholds. It is particle bigger than 0.3 micron and particle bigger than 0.5. And in this case, we did a comparison. Here the difference is higher, but however, again, the interest is in having a good determination of the relative variation of properties and not absolute values. So it was able to provide useful information as we will see in a moment. And now the determination of the boundary layer. We start now with the results. The determination of the boundary layer is important because it allows us, first of all, to identify whether the Picomon observatory lies above the cloud, above the boundary layer. And on the second hand, to divide the properties of the aerosols above and below the boundary layer. And this is one of the technique that I adopted to identify the boundary layer, that is with atmospheric measurements of potential temperature, humidity, specific humidity, and atmospheric reflectivity. And the idea was to find the best matching about these four methods. And then we also used the particle concentration and scattering coefficient profile. You can see that the correspondence of the boundary layer is sharp decreasing the signal, because as expected, inside the boundary layer there is vertical mixing, while above in the free troposphere, vertical mixing, the structure is stable and less polluted in general. This is a thin layer of aerosol above the boundary layer. We will speak of it later, and was a feature that was present in several profiles. And finally, I report again the graph of the boundary layer determination. We can see that the three methods provide comparable results. In green is the results obtained from radio sounding in Graziosa, that is the island are about 70 kilometers, and we see that on average they are smaller as expected than the values that we measured. And so, thanks to the possibility of identification of the boundary layer, it was possible to distinguish the properties of the boundary layer with the ones of the free troposphere. Here we reported the average of the particles inside the boundary layer, inside the boundary layer in red, and outside and above the boundary layer in blue. And we can see that on average, particles in the boundary layer have signal concentration that are higher than the ones in the free troposphere as expected, and also that on average the signal in the free troposphere seems to be steady, except for a few cases like this, in which it seems to follow the signal in the boundary layer. This allows us to make the hypothesis of the fact that during those days an interaction between the boundary layer pair and the free tropospheric one occurs. And this kind of mixing is more evident by analyzing the normalized difference, that is the number of particles in the range 0.3 micron and 0.5 divided by the total number of particles. And this is a measure of the average size of the particles, and we can see that in the 2015, for example, particles in the free troposphere were on average smaller than particles in the boundary layer. This is a specific event of dust that they want to describe because they don't have time, but only to explain why there are these outliers. And it's interesting to note that there are 3 points and 4 points for which the normalized difference seems to be the same. That means particles with the same size, and in this case, these were probably caused by event of mixing of air. In particular, it's interesting to note that these 2 points have values compatible with the free tropospheric ones, and thus this allows us to say that probably it was caused by an intrusion of air masses from the free troposphere into the boundary layer. Moreover, we can see that on average, the 2014 was characterized by particles that were smaller in the boundary layer and bigger in the free troposphere, while the 2015 has the opposite trend. And so, another thing that was evaluated is the scattering cross-section. This was evaluated taking the average scattering coefficient and dividing it by the particle concentration for the channel, for the wider channel, that is the channel that measures particles above 0.3 micron. And you can see that even in this case, the 3 events that we identify like a mixing shows values that are compatible, and this means that particles were not only particles with the same average size, but they also have the same scattering properties, and thus support our hypothesis of a mixing event during those days. These points that are on average, they are always caused by that dust event. Finally, we use the sample meter to confirm this data, and the potentiality of the sample meter is that we do measurements from the sea level up to the top of the mountain, and we can see that on average the aerosol thickness decreases as expected because the clearly aerosol in the boundary layer have concentration that are higher than in the free troposphere, while the Armstrong exponent has the opposite side. I have to remember to you that Armstrong exponent measure, it could be used to measure the size of the particle, and a small Armstrong exponent means bigger particles, while an higher Armstrong exponent means smaller particles. And thus this confirmed the observation. This was also done looking at this graph that shows the Armstrong exponent on average at the sea level in red and at PMO in blue. You can see that on average the values at PMO is higher than the one at the sea level. I also have to point out that these error bars are not error bars caused by error, but they show the data dispersion. Only to make everything clear. Okay, finally, and we want to speak about one event. I don't know if the projector showed each, but in this case, about the cloud, it was possible to see 3 clear layers of aerosol that were more polluted and more dark than the rest of the free troposphere. And I only enhanced the contrast here to make them more clear, and the lines are to show the presence. And the interesting is that they were also measured by the optical particle counter. Here, after boundary layer, we see that the signal increased 2 times. It corresponds to the first 2 layers, and maybe also 3 times, but unfortunately, the modeling finished, so it wasn't possible to go ahead. We can also see that these layers are made by particles that are smaller than the others, and this opened the opportunity to study these thin layer of aerosols that are long-range transported aerosols that are not very well characterized, and that can change the albedo of the clouds, over the clouds significantly, and the possibility to resolve the structure in the vertical structure, that is to measure the thickness of their particle characteristics, is one of the key results of this research thesis. So I don't know with the time how I am, but I come to the conclusion. I can say that we collected several profiles, and among these, 13 of them shows a clear transition between the boundary layer and the troposphere. And analyzing these profiles, it was possible to identify the height of the boundary layer, and this is important since it allows us to say that in those cases, we want to observe we are always well above the boundary layer, and thus to identify the properties of the aerosol above and below the boundary layer. And this allows us to see that the aerosols are effectively different, and also to understand events of mixing that could be used in this case to understand whether the measurements of the Mountain Observatory are effectively representative of the free troposphere or not. Finally, it was possible to resolve the vertical structure of the aerosols above the cloud, that these thin layers of aerosols that are not well characterized, and that will allow us that should be used in order to understand their relative forcing effect. This links me to the final slide about the future perspective. That is a better characterization of these thin layers. In particular, the idea is to use measurements done at PMO in order to understand their chemical composition. Also, SEM and them samples were collected, but the analysis are undergoing at Michigan Technological University. And the idea would be to estimate the mixing state of the particles at different states and to understand their chemical properties. Finally, from these profiles, it will be possible to estimate the relative forcing and heating rate of these layers. Only to help you to remember why it is important to do this, because aerosols contribute to the larger uncertainties on the overall effective relative forcing. That is a measure of how the various anthropogenic drivers could change the temperature of the atmosphere, and these affect our ability to predict future climate and understand the past ones. So this is all. Thank you for the attention. Yes.
I have a question, because it's a pity that you say that you would like to explain what the tendency or why they were some kind of changes. I don't remember exactly the age. I think it was 17. So I have no time to explain this behavior.
The dust event, you mean, sir?
I think it was this one or the last. This one,
no,
for example.
And this you can see that here the ratio is very small. That means it's around 0.5. That means that more or less half of the particles were bigger than 0.5 micron. And this is here outlined with respect to the overall signal. This was characterized as a mineral dust event, probably from Sahara, and the presence of this intrusion of dust into the free troposphere there was also confirmed by measurements done at PMO. In particular, there is an interferometer that allows to measure the concentration of iron, for example, inside the particles, and they show a peaks in the iron concentration. And also here we can see from the technical section that the level is significantly higher than the average, and this is expected since dust particles are bigger, and also they have stronger scattering with respect to absorption.
Other question? Yeah, I have a curiosity where you were characterizing the position of the boundary layer. You were plotting the relative humidity when you were hiking up, And then theta is the temperature?
Is a potential temperature. Potential temperature is a measure, is used to measure the vertical stability. Essentially, is a quantity that is conserved under the vertical condition and is defined. And substantially, this gradient allows to understand whether the atmosphere is stable, neutral, or unstable. So usually, in the boundary layer, it is near zero, while in the troposphere is bigger than zero, and the weight of the boundary layer, in several words, is taken equal to the point of the maximum that corresponds to the maximum gradient of the potential temperature.
There, the theta is to underline.
Okay.
Yeah. Sure, that's your question.
Okay, I do any other, because I do have a question.
Are there special conditions when you take measurements concerning sun irradiation?
Okay, I take measurements when the weather was good. It was also interesting to correlate these measurements with general atmospheric measurements, for example, wind. But we didn't have the instruments to put different anemometers on the slope of the mountains to see whether there was like absolute flow or not. So yes, I did measurements in every condition, only with weather was not possible. But we didn't have the possibility to correlate this with other kind of atmospheric measurement. There is only a weather station at the top of the mountain, but this is not representative of the. It's not said that it is representative of the wind, for example, on the slope of the mountain because they are different conditions.
And also concerning sun irradiation intensity.
And the sun irradiation intensity is expected to rise the height of the boundary layer, for example. Even if even if in here we are near the ocean, and the ocean could be thought as an infinite reservoir of potential capacity of thermal capacity. So the presence of solar irradiation is not expected to rise significantly the height of the boundary layer because the extension of the island is small. So it's not here on the mainland. The presence of solar irradiation rises significantly the boundary layer, giving rise to a daily evolution of it. But on the ocean, we expect to not see this kind of evolution.
I do have a question. So since here during your presentation you put under the carpet the fact that you had actually a very big issue in your long-term observance, that was the determination of the proper elevation. Yeah. Could you comment a little bit about
that? I have maybe a slide in the end. The problem was that we discovered that the pressure sensor was not able to measure properly the pressure. So I had to do a lot of work in order to try to correct this fact. And the problem was okay, during the 2015 season we had a GPS, so we didn't have the problem of derivation. The GPS was not used during the 2014 season, and in this case the only way to recover the pressure, the elevation is from the pressure. You can see here that this is the instrument, the data logger. It is different from the signal that we measure with other independent instruments, and so it is not correct. We developed a procedure that is based on the conversion of the pressure into an elevation. Then, since we know the elevation of the starting point and the elevation of the final point, we were able to adjust the pressure and then the elevation, and then to convert it to a pressure. And this gives rise to this kind of results. And we can see that okay, this was two different kind of reduction that we use. In that we use integration, and we can see that the difference is significantly reduced. Only on the first point there are 9 uncertainty, but in the end we estimate the error to be around 6 Pascal. That converted in elevation is around 50% of the elevation is error. And yes, this is one of the issues that I was mentioning at the beginning of the presentation, to work with not properly instruments, and a lot of work was expended in order to understand whether they were able to measure the proper quantities or not.
And then you make also the case that actually so it was not possible to go up and down in a short time, in the sense that you can go up in the morning and then you have to go down in the evening or in the afternoon. So is it the result affected by the
upward or downward directions or not? So I try to sleep there and then try to get.
Yeah, we also did this. And no, the fact is that maybe in the downward direction we are affected by the fact that we usually go faster, and we saw that the time response of the sensor sometimes was affected by this time lag, but not like. But we did in reality measurement at more or less every time of the day, so we didn't notice any kind of offset of correlation related to the times of the use, because as I said, the presence of the boundary layer shouldn't evolve very much in the day because you are near the ocean. So yes, you can see this. And having the possibility to more profiles in a day clearly would be a better way to understand if there are any kind of variation, but there is a physical limitation.
Okay. Any other questions?
Yes, just a curiosity. Which is the typical fluctuation on the elevation of the boundary layer moved around the world?
More or less, we can see. Okay, we saw the graph. I think more or less 200 meters, depending on the condition.
Okay.
And it also depends on more or less 100 meters during the good days, clearly, because when there was the clouds and that condition.
Independently where you are, it is more or less.
No, it is supposed to be constant. Only the fact that, as I said, if you measure it on free atmospheric condition like with radio sounding, you should have found a value that is smaller than on the mountain because the solar radiation of the mountain is rising on the near the mountain.
Ok, grazie, ma dobbiamo un attimo riunirci, quindi se ci potete lasciare.